Good morning, my name is Juan Carlos Reyes, professor at Universidad de los Andes and Assistant Director of the AIS 600 Committee. Today, together with Sandra Jerez and Daniel Ruiz, we present an executive overview of the AIS 610, a complementary document to the Colombian Seismic Code. This standard establishes technical criteria for the evaluation and seismic intervention of 1- and 2-story heritage buildings made of adobe and rammed earth. This document was developed through a joint effort between the Ministry of Culture and the Colombian Association for Earthquake Engineering, supported by extensive experimental research conducted at various universities. Let me briefly introduce my colleagues. Dr. Sandra Jerez, professor at Colombian School of Engineering and AIS 600 Committee Director, will discuss chapters 1 to 3.
Hello everyone, it's a pleasure to be here with you today.
Dr. Daniel Ruiz.
I'm a full professor of civil engineering at the Pontificia Universidad Javeriana in Colombia. My research focuses on the seismic rehabilitation of earthen buildings, such as rammed earth structures.
Finally, I will return to summarize chapters 6 to 9 and the practical implication of this standard.
Thank you, Juan Carlos. AIS 610 EP17 fills a critical regulatory gap since NSR 10 does not recognize earth as an approved structural material. However, Colombia has thousands of adobe and rammed earth buildings, many declared as cultural heritage. So, Chapter 1 defines the scope and purpose. It provides procedures to evaluate seismic vulnerability and design structural interventions in 1- and 2-story heritage buildings. The goal is twofold: protect human life and preserve cultural and historical value. It establishes a structured evaluation process including documentation, structural assessment, demand capacity verification, and redesign if needed. Then, Chapter 2 introduces the notation and technical definitions required for structural calculations aligned with NSR 10 seismic parameters such as spectral acceleration, base shear, and resistance reduction factors. Chapter 3 is fundamental. It establishes the minimum studies required before intervention, such as historical evolution of the building, architectural characterization, geotechnical investigation, material characterization, and pathology assessment. It emphasizes a multidisciplinary approach involving structural engineers, conservation architects, and heritage specialists. This framework ensures that interventions improve seismic safety while respecting authenticity, material integrity, and cultural value.
Thank you, Sandra.
Chapters 4 and 5 provide the technical and analytical foundation of the standard. Chapter 4 is about materials, and this chapter defines procedure for experimental characterization of adobe units, rammed earth walls, mortar and plasters, reinforcement materials, and extensive laboratory testing was conducted to determine compressive strength, shear strength, modulus of elasticity, and flexural capacity. Chapter 5 is about the structural evaluation criteria. This chapter defines equivalent seismic demand, energy dissipation capacity coefficient R, overstress index as a demand to capacity ratio, and flexibility index for drift control. The method ensures that intervention decisions are based on measurable performance indicators rather than empirical judgment. Experimental validation was critical to calibrate resistance factors and the strengthening efficiency coefficients.
Thank you, Daniel. Chapters 6 to 9 translate research into engineering practice. Chapter 6, Evaluation of Existing Structures. This chapter defines how to calculate axial resistance, shear resistance, in-plane or out-of-plane bending, and overturning stability. This video shows cyclic and dynamic tests conducted to calibrate the proposed equations, using full-scale specimens of piers, isolated walls, and corner walls. Chapter 7. Strengthening alternatives. The code defines approved strengthening systems, for example, timber of steel reinforcement, vertical and horizontal tie rods, steel and synthetic meshes, and diaphragm improvements. Cyclic testing of wall piers clearly demonstrates the substantial impact of retrofitting strategies on structural stability and crack propagation control. The results show improvement in strength, stiffness, and energy dissipation capacity when reinforcement systems are incorporated. Full-scale testing of 1- and 2-story wall specimens further confirm that properly designed retrofitting solutions markedly enhance lateral capacity and deformation tolerance under seismic demands. The following video presents shaking table tests of 1- and 2-story earthen specimens, both unreinforced and retrofitted. A 2-story module is also included, where the effectiveness of the strengthening systems and preserving structural integrity and preventing collapse mechanisms are clearly evident. Chapter 8 presents design of the strengthening. This chapter provides formulas and design procedures to calculate strengthening capacity in compression, shear, and flexure. It integrates reduction factors and strengthening efficiency parameters derived from experimental calibration. Chapter 9 presents pre-strengthening repair. Before any intervention, damage must be addressed, for example, moisture deterioration, cracking patterns, settlements, biological damage. Repair ensures that strengthening measures act on a stable structural substrate. The AIS 610 EP17 document represents a milestone for Colombia. It bridges structural engineering, seismic safety, and cultural heritage preservation. It transforms experimental research into enforceable technical criteria within the Colombian Seismic Code. Most importantly, it provides a scientific basis for reducing seismic risk in vulnerable earthen buildings while respecting their historical value. The collaboration between universities, AIS, Bogotá Institute of Cultural Heritage, and the Ministry of Culture demonstrates how research can directly inform public policy and building regulation. Thank you very much for your attention.